Wow, this is a bit intimidating. So it's my pleasure to be in Waterloo to speak about, to give a talk in this distinguished lecture series from Bill Tutte. I don't know Tutte quite well because I started coming to this department. I mean, it's pretty unique to have a Combinatorics and optimization department. It's the only department, such department anywhere in the world, and also as part of a faculty of mathematics. And so I started coming to this department in the 90s, and especially towards the mid to late 90s, I was an adjunct professor here in Waterloo, and so I came quite a few times. And so I had the pleasure to bump into Bill Tutte from time to time, even though he was not coming on a daily basis. So I've had some brief interactions with him, but it's mostly through his work that I got to know some of the beautiful mathematics that he has done. For the young people in the audience that haven't met Tutte and maybe don't know too much his work, I would really advise you to look at these two volumes, selected papers of Bill Tutte, that were published for his 60th birthday, so almost 40 years ago. And so it's a collection of 60 papers, and many of them, or maybe all of them actually, have like a few pages, 2-3 pages by Bill Tutte explaining, some of the mathematics, but also what went through his mind when he was doing it. And it's quite illuminating to look at it. So I'm sure that there are plenty of copies here in Waterloo, so I would strongly advise you to look at it. So the subject of my talk is line search in polymatroids, and that's joint work with Swati, Gupta, and Patrick Jaillet. But I'll first start by reminding you, because I'm sure that you have seen many of these results, reminding you of some of Tutte's results, and I will focus on the easiest to state, or the most well-known ones. So I was talking about this preface, and the first paper in the series is his first paper, written in 1940. So he was in the late 30s. As you heard this morning, he graduated from Trinity College in 1938 as a chemistry major. And in the late 30s at Trinity College, he interacted with 3 mathematics students, and the 4 of them really brainstormed on quite a few problems, especially a very basic problem of, they had read Harold Stone had read in a recreational mathematics paper about the problem of taking a rectangle and partitioning it, tiling it with squares of different sizes. And there was a question of uniqueness, and so they said, well, if we could tile a square with subsquares of different sizes, then that would be a contradiction to the uniqueness of the tiling. So here is one example of a tiling of a rectangle, and one of the key observations that they made was a way to translate that problem into electrical networks. So if you take, let me maybe do the inverse map. So if you take a planar graph and you view it as an electrical network, so on every edge you have a resistance of value 1, and you take 2 specific nodes and you put a current that goes, let's say, from this node to that node. And so by Kirchhoff's laws, the current will flow through, and you can deduce potentials for each of the of the nodes, of the vertices. So you could say that, for example, that potential is 0, that one is 1, and all the other ones are in between. And you have also currents, currents on every of the edges. Now, if you look at the fact that the difference in voltage is equal to the resistance, which is 1 times the current, means that this difference of potentials is equal to the current going through that edge. So what it means is that if you can associate a square with this edge, the height, so the y-axis is the potential going from 0 to 1. So that vertex of potential P4 is mapped here. And then since you know that the current is the width of this rectangle, since that current is equal to that height, that's indeed a square. And if you think about the current across any of these cuts, by the conservation of currents, you have that the current across is a constant, and that's the width of the rectangle. So from any planar graph, by doing any choice of two vertices, you get one of these tiling of a rectangle by squares. So that's, I guess many of you know that, but it's quite an amazing transformation. I mean, when you think about tiling a rectangle by squares, you would not think about electrical networks. And in the analysis, to try to get a tiling, which is a tiling of a square by squares of different sizes, they actually rely on, for example, the matrix tree theorem that was discovered by Kirchhoff, but in fact that was really one of the key in this paper. So in this paper, after a lot of developments, they got, so that's from the original paper, they got a tiling of a square by squares. And so that was in 1940. So I'd like to show you a little demo. And I didn't do the little demo. It's actually a piece of software that was prepared by Lassi Lovas many years ago. And it demonstrates several algorithms, including several of Bill Tutte. And let me, so this is due not to me again, but to Lassi Lovas. And let me show first the square tiling. So here is a planar graph. And now instead of seeing bottom to top, you should see left to right. So sorry, I should turn my screen, but that's not possible. So this is a planar graph that's bottom and top. And now suppose that everything is has a resistance of 1. So, and then we'll let equilibrium get. And so this represents the potentials from 0 to 1. Instead of being completely collapsed on the line, on this picture, it's actually just a tiny bit spread. But then you can associate a square to each of these. And you get these squares. So, for example, these edge, that was a certain current. The current was, the length of that edge was the difference in potential. And so that's both the current amount and the difference in potential. And so you get a tiling, of this rectangle. Now, you can choose the graph. You can try to choose the graph appropriately. And so what Tutte and his colleagues did was to define some symmetry operations that allow you to get a graph with the right properties. And if you, actually there's some nice animations that to get from the graph to the tiling. So let me show it with another graph, which is, I think, called squares 1 open. So if you take this graph and then you do move and then squares and then you show height, so that's the smallest tiling of a square by squares. I don't know if that's on that's the one that's in the plaque that was just shown or not. I don't know if I didn't check if that was the same. This seems bigger than the one that was there. So let me, while I'm playing with this software, let me show you another result of Bill Tutte on how to draw a graph. So that's another classical result. So suppose you have a graph, and suppose that you pin down several of the vertices in a convex position. So you take a cycle and you pin them down in convex position. And suppose that on every edge now you put a spring. And so you look at the equilibrium, and now at the equilibrium, every vertex will be equal to, will be the average of its neighbors. So when you let that go through, so if I do move, so that's the equilibrium, and you get a nice, so again, this is due to Lassilova's. Oops, something happened to, this is strange. Oh, it's, okay, good. That's Microsoft, sorry. So you get an equilibrium, and so what Tutte showed was that if you have a planar graph, which is 3 connected, and if you fix 3 vertices, then or if you fix a set of vertices of a face, the embedding will be a straight line embedding that's planar, and you can choose any of the faces to fix. So you can, so for example, you could take 3. You can take 3. I mean, if it is not 3 connected, you can add edges to make it 3 connected. So let me show you some maybe bigger graphs just as we are doing this. Planar 7, let's say. Good, open. And so you let it settle, and at equilibrium, you get a nice planar drawing. So let me go back to, we could play for the rest of the talk, but I'd like to, I mean, it's a pretty, I mean, I'm not showing you all the capabilities of this piece of software. It's quite nice, actually. So let me, so this, so that was How to Draw a Graph from 1963, published in 1963. And in fact, this group of four undergrads, Bill, Leonard, Arthur, and Cedric, so Tutte, Brooks, Stone, and Smith, ended up spending a lot of time together and doing mathematics and poetry and other things. And so they started writing some articles actually under a pseudonym of Blanche Descartes. So their initials were 4 of the letters of Blanche, so Bill Tutte continued using that pseudonym in many occasions. And so, for example, as was mentioned earlier today, he loves the 4-column theorem and has lots of results about coloring in graphs. And when when the proof by Appel and Aiken of the Font-Collant theorem came out, he published in the Journal of Graph Theory. It's actually pretty funny to look at that issue. It's a big page, and on the big page there is just this in the middle of the page on some recent progress in combinatorics. So initially I thought it was going to be a real article about the Font-Collant theorem, but it was just this. So very brief announcement of it. After the war, so it did not publish during the war. So after the war, and we heard lots of stories about his code breaking at Bletchley Park during the war. So after the war, he one of the first papers after the war was a very classical result, which is known as Tutte's one-factor theorem, which you can try to read this, and you can try to read the entire paper, but you'll see that the terminology he was using at the time, I mean, graph theory was really at its infancy at the time, and so the terminology was not was not yet well established. So he's really talking about zero simplices and one simplices from edges and so on. And so really from simplicium complexes terminology. And so this has to be, in the modern terminology, it says that a graph G has a perfect matching if and only if for every set of vertices, if you delete these vertices, that breaks up the graph in at most S odd connected components. Very classical result. Tutte got interested in this problem because he was reading Peterson's theorem that says that a bridgeless cubic graph has a perfect matching, and he could not quite understand that proof, so he ended up trying to reprove it and at the same time extend the result. And later, Bunge, we got a bound on the a tight bound on the size of the largest matching, and so that's known as the Tutte-Bunge formula. And this is really when matching theory really started, and of course one of the later development that was quite impressive and done also here at Waterloo was Jack Edmonds' matching algorithm and the description of the matching polytope. Now, one thing that I find pretty amazing, I had never looked at this paper. I mean, I've known this result for quite some time, but I had never looked at this paper. And it's only this week, or maybe even 3 days ago, that I need to apologize for that, but that I looked at it, and it's not at all the, I mean, I can give you several proofs of this, but not at all the way I was expecting that Tutte had proved it. In fact, he was in his work on tiling a rectangle by squares using electrical networks. As I said, the matrix 3 theorem came up, and so that's, you take the Laplacian of the graph, you remove a column and a row, and then the determinant of the resulting matrix is equal to, for example, the number of spanning trees, or if you have resistances on the edges, it's the sum of the conductances, the sum of the product of the conductances on all the spanning trees of the graph. So he was quite impressed by the fact that there was these, and I'm also very impressed by the fact that this determinant formula comes up. And so he was trying to look at other cases in which determinant formula has come up. And so he came up with this Pfaffian these, I mean, he saw the notion of Pfaffian, and then realized that if you, with a graph, you assign you have a skew symmetric matrix that corresponds to it, in which the entries are indeterminates, then the corresponding Pfaffian, so the corresponding Pfaffian is actually a sum over all perfect matchings of the product of these variables times a sign. And so that vanishes if and only if the graph does not have a perfect matching. And so and you can also easily see that the rank, even though it's not explicitly said in that paper, you can also see that the rank of that matrix is twice the size of the maximum matching. And a lot of result was built on that, first by Lassilovas in the late 70s, and then Jim has some beautiful results to make. So Lovas was a randomized algorithm based on this, and Jim Gill showed by properties of subdeterminants that you could make it deterministic. Now, when I teach combinatorial optimization, I end up covering lots of results of Bill Tutte, and it's probably the single, I mean, so I cover so many results of him that I decided to list some of the results that I'm covering in a typical introductory combinatorial optimization class.
Will you get to polymatroids?
I will get to polymatroids, yes. I will. That's a good question. I will get to it eventually. So but I'm enjoying reading old papers as well. So the question of Tutte was when does a graph have k edge connected, k edge disjoint spanning trees? So it's in a different, it's stated differently, but that's the result, that it has k edge disjoint spanning trees if and only if for any partition of V into L parts, the number of edges between the parts is at least the minimum that's clearly required. And so that actually can either be proved. It's actually almost more difficult to prove it in the graph case. It's much better to generalize it to matroids, and then and so there's this very nice result of Jack Edmonds on the matroid partition theorem that you can derive it. So Bill Tutte did a lot of work on matroids, and it would be hard to summarize it, but at least I see that one person in the audience is quite eager that we move to polymatroids. So maybe I'll skip some stuff here. So let me go to submodularity. And so a submodular function is a function on all subsets of a ground set V, such that this inequality is satisfied for any two sets. And we're assuming that the function is not given, the value of the function is not given on any subset, but if you give me a subset, then I'll give you the value of the function on that subset. So it's an oracle that we use. And it's a really key concept in combinatorial optimization so modularity dates back from very early on, the 20s or the 30s. It does appear very often in Tutte's work, but then it's not, the term is not used of submodularity. But certainly it became quite popular in combinatorial optimization after the work of Edmonds in the late 60s. And it can be viewed as a discrete analog of convex functions. And the most classical example is the rank function of a matroid. So that satisfies submodularity, but also, for example, the cut function of a directed graph or undirected graph. So what is a polymatroid? You are given a submodular function f, and you look at the polyhedron in which you have one inequality for every subset of vertices, and you get that the sum of the xi over that set is at most the value f of s of the function. So it's some people refer to it as the extended polymatroid because I don't have the non-negativity constraint. So it's the it's a polyhedron and not a polytope. And there are lots of nice properties about polymatroids. You can optimize over them. The vertices and the faces are very well characterized. And if I give you a point x and you'd like to decide is it in the polytope or not, so one thing you could do is you could try to minimize over all sets S f of s minus x star of s. So that's the modular function, the linear function that takes the value sum of x star e over e in s. And so this function is also submodular. And so checking if a point x star belongs to P of f is equivalent to minimizing a submodular function. But you don't want to try to find the minimum. You don't want to try. You don't want to look at all the sets. So the first major development there was an algorithm by Cunningham, which would work, for example, for matroids, but it would not be. It would be polynomial if the function takes small values. So if, for example, if the encoding is in unary, but otherwise it's a pseudo-polynomial. And then there were two distinct progress later. One was by Groche-Lovász and Scriver using convexity and using the ellipsoid algorithm. So that's one path. And then Lex Scriver and Iwata and Fleischer looked back at Cunningham's algorithm and managed to make it, add some additional components and make it a polynomial, irrespective of the size of the submodular function. And there were some later development, improvement of these algorithms of Scriver and Iwata based on whether you want to have only fully combinatorial ones. And so let me not get too much into that detail. So here's the problem I'd like to discuss for the rest of this talk. So I'm given a polyhedron. In my case, it's going to be one of these polymatroids. And I'm given a point in the polytope, in the polyhedron, and I'm given a direction. And I'd like to know when, if I do a parametric line search along that line, when do I exit that polyhedron? So in the case of a polymatroid, I can always shift it so that my point x star is at the origin. That remains a polyhedron, a polymatroid, so that I can really assume that x star is 0 in my case. And then what I need to do is I really want to know if I go in the direction A and I look at lambda A, I'd like to know if lambda A is in that polymatroid. So that amounts to checking, to finding the largest lambda such that this is non-negative for every S. And so what I'd like to discuss in this talk is two different cases. So the case in which A is non-negative has been well understood for a long, long time. And I'm not going to discuss that too much. I will just have one slide on this. But so the major case in this talk will be on the general case in which A can take negative values as well. So, and the way that the way that we can do it, the most natural approach to do this is to do the following. We look at lambda as a function of lambda, f of s minus lambda a of s for a given set S is just a linear function. So that's f of, let's say, for some specific set S1 minus lambda a of S1, that's a linear function. And then I have another set, and then another set, and so on. And I can take the lower envelope of this, so that would be maybe this. And what I can do to find, so what I'm looking for is that lambda star, which is the largest lambda for which that function is non-negative. So what I can do is I can take a fairly large lambda, let's call it lambda 1, and then by submodular function minimization, I can find the set S which minimizes f minus lambda 1 times a, and I get this point, and then I can trace back, and this would be my second lambda, lambda 2. And then I repeat, I minimize the function f of s minus lambda 2 a of s, and get this set, and then continue. So that's the most obvious algorithm that you could consider. And so that's what I wrote here. Every time you SI is you have a lambda I, and SI is the minimizing set, and then you set the next lambda. This should not be G of Si, but should be A of Si. So it should be f of Si minus A of divided by A of Si. Should be the next lambda I plus 1. Now, what's easy to see is that when you do that, indeed, the lambdas go like on this picture, they decrease, and eventually you'll get to lambda star. And you can also see easily that the slopes are monotonically increasing or decreasing depending on whether you see them as positive or negative. And also that these heights are monotonically decreasing. So that's obvious. But the question is, how many iterations does it take? So what's t? How many iterations does it take? Now, in the case in which A is non-negative, and that's the slide for A non-negative, it's very easy. And why is it very easy? It's because of the following. When I look at, I will be looking at f minus lambda 1 times A, that's one submodular function. And then I will look at f minus lambda 2 of A, that's another submodular function, and so on. These are very much related to each other. So in fact, if I define Li to be one of the submodular functions, they form what's known as strong quotients. So two submodular functions, Lj and Li, form a strong quotient if for any two sets, the increase in one of the submodular functions on these two sets is lower bounded or upper bounded, depending on which one you consider, by the other one. So that's the definition of a strong quotient. And it's easy to see that if you have a bunch of strong quotients, then the minimizers form a chain. The first minimizer, S1, contains the second one, contains the third one, and so on. And in the case in which A is non-negative, you get that these submodular functions form a sequence of strong quotients. And so you get this chain, and finding this chain can either be done by, so the length of the chain is at most n, and so you can either find that minimum by n submodular function minimization, or you can also actually, a sequence of strong quotients can be sped up and can be done in time roughly of one submodular function minimization. So that's many of the algorithms for submodular function minimization can be modified in this case. The problem is that the case in which A is not non-negative, this does not hold. It's not a sequence of strong quotients, and so you lose this chain result. And so the question that we're looking at is to try to find a bound on the number of iterations. And there was no bound known before, so not even, I mean, just a trivial exponential bound was known, but there was no bound known on the number of iterations of Newton's method. And in fact, I should say that one way to compute that lambda star without using this discrete Newton method is to use what's known as Megiddo's parametric search technique, but that's really prohibitive. So, I mean, you might say, of course, you might say, well, why don't you use binary search to compute that lambda star? We could use binary search. The problem is that the stopping criterion would depend on the size of the submodular function. If my submodular function can take extremely large values, then the problem is that binary search might take, you don't know exactly when to stop. And so there is no strongly polynomial bound on binary search. So the only other way of getting a strongly polynomial bound was to use Megiddo's parametric search, but that's too costly. So we prove a quadratic bound, and there are two main ingredients. So let me first mention the following, that when you look at Newton's method, and so suppose at one iteration you use, let's say, 1 lambda I, and then at the next one you get this slope, and then you get that slope. It's very easy to do, I mean, to see. I could do it maybe in 5 seconds, but I think for the interest of time, I just want to mention that one can show the following, that the ratio of two consecutive slopes plus the ratio of these heights, so the heights at lambda I and lambda I plus 1, can be shown to be at most 1. And that's actually quite nice, because it means that either this one decreases by a factor of 2, or this one decreases by a factor of 2. So either the slope decreases by a factor of 2, or the height decreases by a factor of 2. So the analysis of this quadratic bound will come from two pieces. So the first piece is the following. Let's just think about the slope. So the slope, what is the slope? The slope is this A of S. So it's the sum of the, so over SI, so it's the sum over the elements in SI of AE. So how many times can the slope decrease by a factor of 2? So if I give you a universe of n numbers, how many sets can you create that satisfy this? So the first thing you might try is to say, well, how about if I take the powers of 2? If I take the powers of 2, each singleton can be viewed as a set in that sequence, so I get a sequence of n sets. Now, if you think about it 3 more seconds, you'll see that, well, if A is non-negative, that's the best you can do. You can never get more than n sets. Is it the case also for n, if A is not non-negative? What do the young people think? Can you do better than n? So Ratzik showed that you could you have an upper bound of n squared log n. And then I improved that long time back to half n log base 2 of n. But there was still no lower bound. And so there was still the question whether p could be under n. But then there was, I gave that once as a problem set in a class. And there was a postdoc that came with a solution. So that was quite nice. Using a Fourier analytic construction. And he showed that indeed this bound is tight. So this is somewhat unbelievable. So I'll show you one such construction. So if you take a Hadamard matrix, and then you carefully choose the powers of 2 that you put in the right-hand side, and then solve for h n a is equal to b, you would get, for example, these numbers. And so if you remove the first line, you already have 7 sets that grow quickly by a factor of at least 2. But you can add 5 more sets. So if you look at these, the incidence vectors of these rows, you can get 5 more sets that go in between and that increase by a factor of 2. So in general, you can get half n log n, and so that shows that in your analysis of Newton's method, it's actually, you don't have too many iterations in which the slope decreases by a factor of 2, at most n log n. But there could still be a lot of iterations in which it's the submodular function value decreases by a lot. And it's not actually the same submodular function that you have here, and you have here, and you have, so you have different submodular functions at each lambda. But here is another puzzle. So suppose I take a submodular function, and suppose again I have a bunch of sets, and they grow quickly. They grow by a factor of b, let's say. B being, let's say, 5 or so. So how many such sets can you have? How much degree of freedom essentially do you have in a submodular function to, can you make it big on lots of sets? What do you think, Jack? So it's actually, the best you can do is n plus 1 choose 2. So you can find a geometrically increasing sequence for a submodular function of size n plus 1 choose 2, provided b is at least 4. If b was smaller than 4, so if the power was, so if the base was lower than 4, in that case you get an extra log base b of 4. So, but this can be achieved, and it can be even achieved by a very simple submodular function, which corresponds to a directed graph. So, so in fact, I mean that. I'm just watching the time a bit. So how do we show this result? Well, it's actually not that complicated. What we do is, the first thing we do is we look at, so what is a ring family of sets? A ring family of sets is just a collection of sets that's closed under taking intersection and unions. And so Birkhoff's representation theorem shows that a ring family can be very compactly represented by a graph. So you have a directed graph, and you have also two specific sets S and T as a subset of T. It should be S and T here. And then a set is in your ring family if and only if it contains S. It's a subset of T, and there are no edges leaving on in your set. So in this diagraph. So there is a nice correspondence between ring families and such directed graphs. And what you can see essentially is that if you have a bunch of sets that grow quickly, the next step, the next set, cannot be in the ring family that's generated by the first. So the I plus first set cannot be in the ring family generated by the I first sets. And so then the question is then, if you have such a collection of sets that one set is not in the ring family generated by the previous ones, how long can that sequence be? And so that's that we can show by using this Birnkauf's representation theorem. We can show that that's at most n plus 1 choose 2 plus 1. And so that was essentially the same n choose 2. And so again, this can be attained if you look at this sequence of sets. So these are sets ij such that the second index never decreases, and when the second index is the same, then the first index is also increasing. So essentially from these two pieces, the fact that you have at most n log n sets in which a linear, a modular function or linear function increases geometrically, and these increase from some modular function when you have still to do some work, but when you can put them together, and then you get that the number of iterations is n squared plus some terms that are like n log square n or something. But this is, I do not know whether this is tight, and one of the big questions is whether actually in this general case for general vector A, whether we could still get a linear number of iterations. So I don't know if the discrete Newton method applied to an A that's general might still give only a linear number of iterations. I do not know whether that's true or not. So the 50 minutes are over, so let me stop here, and thank you.
Hi. So the result you talked about is for the polyhedron or extended polyhedron. What about for the base polyhedron? Have you considered that case?
So so for the you mean so adding x of v is equal to f of v. So for the base polyhedron, the same will hold actually. So you can do a transformation to get the same bound in that case, yeah, the same result will. I mean, possibly you might be able to. I mean, I doubt one might be able to get a better bound, but certainly the n square bound holds as well in that case.